So here we are with an design of experiments in which we have 4 factors: enzyme concentration, temperature, pH, and stirring, yes or no. And we're in a situation where we only had one measurement for each treatment combination over here. This is what we call a non-replicated design, or unreplicated. So we did a regression analysis and we got all the coefficients, the 16 coefficients in our model. But because we only had 16 pieces of data, we could not compute the standard error, the T statistic, and the p-values. In other words, we were not able to, or Excel was not able to evaluate the significance of these effects. So what we did was we made a normal probability plot of the effects. And we determined just by looking at this plot that these effects here seem to be significantly different from 0. Maybe this one too. And that's the ones I've put in yellow here. This one may be too. That's this one here. And the 3 ones at the other end corresponding to these effects here. They seem to be significant. And if you notice on the list here, all the insignificant effects are third order, or at least you could say the third order effects are all insignificant, and the fourth order as well. This is not a coincidence. This is often so that the higher order effects, such as BCD, ABC, ABCD, are insignificant. That is to say that the true value of these effects is 0. The only reason we get something that's not 0, -1, -0.375, -0.25, and so on, is due to random variation. So we can exploit this fact. This is also called the sparsity of effects principle. We exploit this fact, the sparsity of effects, that is to say that higher order interactions have 0 effect. We will exploit this fact because that gives us an opportunity to use these data here for the higher order effects to estimate the variance of the experiment here, of the response. So what we will do is that we will make a variance estimate. Sometimes we call that sigma hat square. And that would be the sum of the higher order effects, I'll call them E for effect, minus the mean, which we assume to be 0, right? Squared, divided by 1/5, because we have 5 of them. 1, 2, 3, 4, 5. So I'll take these effects, subtract their mean, but my assumption is that the mean is 0. Square that, sum, and divide by 5. That would give me the variance of these effects here, and that would be the variance in the, that's our estimate of the variance in the response, in the y value. So once I have that variance, I can use that to find the standard error, or the standard deviation if you like, which is the square root of the variance, like that. And that's the one that Excel couldn't compute over here. And once I have the standard error, I can compute the t value for each effect. Let's just go to the Excel sheet here. So once we have the standard error, we can compute the T statistic here. Excel put in a number, that's just a random number. I don't know why it's writing that. It's not able to compute the T statistic here. And that would be each effect minus 0, because that's the hypothesis. That's the null hypothesis, that the effect is equal to 0. That's what we're testing here, divided by the standard error. That's our T statistic for the ith effect here. And then we can compute the p-value for each effect here, which would then be just like normal p-value for t tests. 1 minus the cumulative t distribution with 5 degrees of freedom evaluated at the absolute value of the test statistic. So we're going to do that in Excel just to make sure we understand. First of all, we find the variance estimate. We use that to compute the standard error here, and we use the standard error to compute the test statistic. That's this column here. And then we use the test statistic to compute the p-values. That's this column here. So let's do it in Excel. Just do like that. And move this over here. Like that. Right. So, first of all, we want to do the variance estimate. That's, according to the formula here, that's 1 divided by 5, because we have 5 higher order effects. And then we need to take the first effect here, that's BCD, minus 0 squared. You don't really have to subtract 0, but I'm just doing it for clarity. The next one is the ABC, minus 0 squared, plus ABD, minus 0 squared, plus, ACD. Could easily make a mistake here. Minus 0 squared, plus ABCD, minus 0 squared. And we'll close the bracket here, and that gives us the variance estimate. And then we need the standard error, which is then the square root in Danish kvadratroot of the variance. Like that. So now we have the standard error. So I'll just copy that to this row here. So I'll take a copy and I'll insert just the number, not the formula, like that, and copy that all the way down here, like that. So it's the same standard error for all the coefficients here. Now we can compute the test statistic. According to this formula, it's just the effect minus 0 divided by the standard error. So the effect, that's this one, minus 0 divided by the standard error. And I'll make a copy of that all the way down here. And now we can compute the p-value, which according to this formula here is 1 minus the t distribution, in Danish t-fordeling. So in English, t distribution, and we take the absolute value of the test statistic, and it has 5 degrees of freedom, and we write true, in Danish cent, to get the cumulative distribution function. There we go, and we make a copy of that all the way down here, like that. And let's just look at now we have p-values in order to find out which effects are significant. Let's just select the ones that are, or let's just mark the ones that are significant, like that. And as you can see, these coincide completely with the ones I estimated to be significant from the plot, except BD. I wasn't really sure about the BD, but it turned out that it's actually significant, at least at level 5%. So that's using the sparsity of effects principle to estimate quantitatively whether or not the effects are significant.